Welcome back to the IB Chemistry May 2025 TZ2 Paper 2 exam walkthrough. Continuing on with this question number 3B for the SL paper, though this is also in the HL paper. And we are seeing that this phosgene gradually decomposes in the environment. So, in just the water vapor that's in the air into this carbon dioxide and hydrochloric acid. And so this part one is saying to suggest how the rate of this reaction could be followed at a constant pressure. And so when we're thinking about how to track a rate of reaction, there's a few things that we need to consider because there's a few techniques we can use. Is if there is not a gas and then a gas being produced that's not hydrogen gas, but something like CO2, because we do have CO2 being produced here, we could use something like a mass balance. However, we have gases on both sides here, so that's not an option. If there is a color change, that could be something like colorimetry or something like that, right? However, if we look at all of the details here, there is nothing that shows that this phosgene or anything else in this reaction is colored. So that's also not going to be an option. Another option would be if this were an acid-base type reaction, then you could kind of use pH. However, that also doesn't seem like something that's happening here. There doesn't really seem to be any neutralization happening. There's not really a conjugate acid, conjugate base kind of pairing happening. And so another thing that could be done would be is the one that is going to make sense for this one is pressure, because we have gases on both sides, and specifically on our reactants, we have 2 moles of gas compared to 3 moles of gas in the products. That is something that we can use. So we are going to say here that this would be a change in pressure. And we would expect the pressure to increase as the reaction progresses because our moles of gas is increasing. Okay, so that was what we would expect to see. With pressure, anytime that you can do a change in pressure, you can most likely do a change in volume. So that also would be an option as well that you could do. But it would just be kind of the inverse because pressure and volume are inversely related. Okay, so this part 2 is to outline why some collisions between reactant molecules do not result in a collision, a reaction occurring. And so there's 2 marks for this. I feel like that's kind of quite important to note. And so this is collision theory. So collision theory requires that 2 things is that 1, reactant particles collide with energy that is greater than the activation energy, and 2, that they collide with the correct mutual orientation. People forget the orientation, but it's important. Orientation, don't forget it. Okay. And so those 2 marks directly correlate. So the first reason would be if the energy, kinetic energy of the particles, is not greater than or equal to the activation energy. Okay. So that would be a reason. So if it is not greater than, we don't have enough energy. So not enough energy. And I would say for 2, this could be and or in this scenario, because either you need to have both, not just one or the other. So and or incorrect orientation. Okay, so those would be those 2 reasons there. For this part 3 is we have to sketch a Maxwell-Boltzmann distribution curve at a higher temperature than the one shown. So we have one here, which is at a lower temperature. And so you can see the probability of the particles having this energy is really high at the beginning, and then it slowly decreases as that kind of happens with the energy at this temperature. And so if you have a higher temperature, then the curve is going to shift to the right and be lower. Okay, so it's going to be to the right. That is a terrible curve. Okay. And it has to start at the origin to the right and lower. And then specifically our plateau has to be higher. Okay, because the area under the curve at the activation energy, so I'm going to put like EA here. So this area here has to be more for a higher temperature because we're not changing the activation energy, increasing temperature. I believe this was a problem in paper 1B or maybe paper 2. I don't remember. It's been a while. I've been doing these videos for a hot second now, and I'm kind of losing my mind. But there was a paper, and or there's a question already in this exam about how temperature affects the rate of the reaction. So we already covered that it does not affect the activation energy. It only affects the portion of particles with enough kinetic energy. Okay, so it's that area that we're changing, not the activation energy itself. And so that's why only the shape of the curve changes as it becomes to the right and it becomes more broad compared to sharp. The lower the temperature, the more sharp the curve is going to be because less particles have that enough kinetic energy. Meanwhile, the higher the temperature, the more broad that curve is going to be because the higher this area is going to be. Okay. And so that would be a thing that would be in this mark. And so I'm just going to put like T2 there just for funsies. So it has lower and to the right and that activation energy shown. And then part IV, part 4, does elaborate upon this. And this now wants us to explain why the rate of the reaction increases as the temperature increases and to annotate that diagram. So we already annotated that diagram with the activation energy. And so we're also just going to go ahead and put there greater percentage of particles with the EK greater than the EA. So we're going to put that kind of there and show that area there. They're going to explain is we're going to say the temperature increases the energy, allowing for more EK greater than EA. Okay. And so this is going to be one where it's 2 marks. And so one of them is going to be your annotations, which is most likely just let me double check this. Yeah, where it is just having the activation energy indicated. And then you just need to have the explanation about the proportion of the collisions. And so the curve for the EA part of the mark is not for the part 3, it is for part 4, if that makes sense. And then part 5 is going to be to describe 2 observations that confirm that a solid added to the reaction mixture is acting as a catalyst. Okay. And so this is one where I feel like this one is a bit more difficult for SL students because they don't learn about multi-step reactions. Okay. And so I'm going to give you some background info with that. And now that I know that this is a question SL students have to answer, I might also incorporate into my own teaching and lessons as well. Is that catalyst, like they provide an alternative pathway to allow this reaction to go faster. And it says, okay, so a solid is acting as a catalyst. And so one of the big things in an overall equation, so in a multi-step reaction, which SL students aren't required to know, is that whenever you have like step 1 and step 2 is that your catalyst goes into the reaction, but then it is regenerated. Your catalyst is always regenerated. It always comes back out of the reaction. And so to confirm that a like solid is a catalyst is that the solid would still, it would not dissolve. Because the catalyst has to be regenerated. Okay. So it has to go in and it has to come out. Okay. And so it would not dissolve. That would be one of the observations that it is acting as a catalyst. And then the other one would be the more obvious, which would be that the reaction rate would increase. Okay, so those would be the 2 things that would confirm that it's acting as a catalyst in terms of visually what you would see during the experiment. Okay, I'm not gonna lie, I kind of have beef with this question for SL students. I do think it is more HL oriented, but you know what? It is what it is. It was on the exam, so now we can assume that you need to know it in the future. So know that catalysts are always going to be regenerated. So regardless of its state of matter, it's always going to be there at the beginning and at the end. It's not going to really change in terms of what you're looking at. Okay.